So last day we couldn't do the class, right? Okay, so this month we'll arrange some extra classes. And Vatsala told that she won't be able to come, so she can watch this video, right? And likewise, if you also may not be able to come, just let me know. I can upload the video, and meanwhile we'll just do you know about Skype? Do you have that account with you? No. Okay. So I'll just put it to the group how you can download the Skype. You have an iPhone or Android one? Android one. Okay, so you can just download it from the Google's Play Store. And these days you can't configure it from the mobile. If you had an account already from a mobile, we can use it. We can recover that account. If not, we can make one from a new email. These days they are not allowing to create one from the phone number for the Sri Lanka. So we'll configure that as well, so that if there's a chance that we could do an online class, we can do it like that. Maybe if you are arranging some extra classes, you can join it from your home in the evenings as well, or maybe at the night, right? If needed. All right. So today we have a new lesson to discuss. Before that, we will just see some doubts if you have. 40 seconds. Okay. It says the part 1, explain how the internal diameter of a capital tube can be obtained by a mercury thread and the traveling microscope. I think you can do it, right? That part you can explain. Okay. Calculate the internal diameter when the length of the mercury thread is 8.25. The mass of Hg, that means mercury, used was 89.6 milligrams, and the density is this much. Should we convert these centimeters? Yes, exactly, because you can see here the density is given in kilograms per cubic meter, that value. So it is 18,600 kilograms per cubic meter. So the equation will be D is equals to, what is that? 2 root, actually it's 4, but you can write 2 like that. M pi rho L, right? Yes. So this is the mass. So we should measure that one in kilograms, so that the density is given to be in kilograms per cubic meter. So that kilograms and kilograms cancels off if both are them at the same unit. And you have this cubic meter. If this one in meters only, the 1 cubic meter, that -3, cancel off to -2. That -2 goes up, then it will be m squared, which is +2. And you can see this is a constant, and the kilograms and cancels off. The only unit, I'm just talking about the unit, right? The only unit that will be there inside the square root will be meter squared then. You get it? Yes. Then taking the square root, it will be just meter. To cancel off those units, all those have to be at the same SI unit. So which means you should convert this one to meters. Yes. So if you do the substitution, it will be like this. D is equal to then 2 root. M is given to be 89.6 grams, so which means 10 to the power -3, that is in kilograms. Dividing by 1000, I can indicate like 10 to the power -3. Are you okay with that? Okay. Then we have this one, phi to be 22/7, or you can substitute 3.14, and into 13,600 into 8.25, that is in centimeters. We should divide it by 100 to make it meters, or you can put 10 to the power -2. Right, now these zeros cancels off. Now let me write the 7 up. 2 root 89.6 into 7 over 22 into 136 into 8.25. Also, we have 10 to the power minus 3 inside the square root. Do you know how to simplify this? Yeah, you tried with the log? The other question? Okay, so are you okay with applying log? Okay, okay. Yeah, you can copy down up to here if you need. And you can do the simplification. It's 42. This is question 42. Okay, I think you can do the simplification, right? We'll just proceed. You can leave some space there too. Okay, do it. What else? For the third question. Uh, the alignment of the crosswires of a traveling microscope for different images are given. They need to be properly adjusted to adjusted on the image to get the reading. Write the direction which the traveling microscope need to be moved to obtain each A, B, C and D correctly. Okay, so right, it's asking which direction you need to move it. Now the part A is given like, okay, so these are the cross wires like that. Okay, so it took some time, but it is approximately how it is given. Okay, like that, right? So if you are making, if you are like focusing to get the diameter, we should focus it maybe on this point and this point, and also this and this, right? So you can just use the vertical scale to first focus in on this point, let's say M1, and you can use the M2. This is from the vertical scale, and also you can use the M3 and M4. Take those two readings from the horizontal scale, which means you can focus on this point and you can move it up, and you can take the second reading and you can take the vertical diameter here, D1. Also, you can take the horizontal diameter, like focusing on this end of the circumference and move it to the other side and the other point, M4, and you can take the horizontal diameter, D2, and maybe you can take the mean diameter, you adding them two and divide by the 2. Okay, so what's the correction that we need to do in this A? Which side it need to be moved to have this? It feels like we need to move it to this side, right? That's what we need to do. We need to move this crosswise to this point. But we know that it is a traveling microscope. In the microscope, the images are getting flipped. So if you are moving it to this point, will it move to this side? No, right? It moves to the other side. So if you need to move this one to this side, the opposite thing that we need to do. We need to move the traveling microscope, yeah, to the opposite side. Which means you need to, in the A, you need to move it to the left or right. Feels like we need to move to the left, but we should move it to the right. Then this goes to the other side. Okay, so for the A, it will be to the right. Should move it to the right side. And the B is kind of this, right? We should obtain this, the upper reading. It feels like we need to move it to the left again, which means to the right. Then the C, which will be this reading we need to take. To take it like that, we feel like we need to move it to the down, but it is getting flipped, so we need to move it up. The other case, it's okay, right? We don't need to, yeah, we don't need to move it because it's kind of aligning with this. Exactly, yes. Okay, now we're gonna do this 44th question. Do you have any other doubts? Okay, so we're gonna do this 44th question together, and we'll have a recap of all the measuring instruments that we have learned, putting it to this. Okay, so it says write down the suitable measuring instrument to take each of the following lengths more accurately. Right? We should indicate the most suitable measuring instrument that we can take the accurate reading of each of these lengths. Okay, let's see about the A. We should think about all the 4 measuring instruments, and we should write which is the suitable one. to take the A? Yeah, meter ruler can be used. And is that, yeah, traveling microscope can be used. What else? What about vernier caliper? We may use that one, right? We can just extract that external jaws and maybe you can fix that, but the external jaws are not going that much far. But let's say it's a small one, so you can extract the external jaws and you can make it, right? It's like this, kind of like your pencil box. So maybe you can take it like that and can extract the two outer jaws and you can measure the length. So we have three measuring instruments. As you said, the meter ruler and traveling microscope and the vernier caliper external jaws. So out of those three, we should write just one. What is the suitable one? What is the most suitable one to take it much accurately? Yes. So meter ruler compared to the meter ruler and the vernier caliper is the best one because we know that the least count is smaller than the meter ruler. Meter ruler, the least count was 1 millimeter. But the vernier caliper, we can go up to 0.1 millimeter. And you said about the traveling microscope. Can't we use the traveling microscope here? Yes, we can. But what's the common thing with the vernier caliper and the traveling microscope? Yeah, they both are having the same least count, right? So traveling microscope, we just need to focus it and we need to slide it, right? All the things we should do. But when it comes to vernier caliper, we can straight away take it and extract the outer jaws and you can quickly take the reading, right? So what's the best thing there? The vernier caliper. Okay, we'll write it. Vernier caliper and you can write the even within brackets external jaws. Okay, then the B. B is you can just flip the entire thing upside down. And what sort of a measurement is that B? Is it a length measurement or, I mean, a length, breadth or a depth? Could be a depth, right? You can flip it like this. You can turn it from here to here, right? And you can see that the B is kind of a depth measurement. Okay. Then, when it comes to depth measurement, what are the things that we can use? Yeah. Spirometer also can be used. Good. Now, out of them two, which is kind of suitable here? Vernier caliper. Yes. Why not the spirometer? It's having a least count which is smaller than the spirometer, the vernier caliper. No? Yes, yes, that's the thing. Good. So when you are using that spirometer, there are three legs. So there should to be a place to put those all three legs, and you can send the middle screw downward. It could be used to measure depth of a hole or something, but when it comes to a depth of an edge, it's better to use the depth rod of the vernier caliper. Okay, we'll write that. Good. Vernier caliper, depth rod. Okay, then the C. What is that C? Yes. Can you identify the C? What sort of a measurement that we need to take? Yes. It's like a rectangular shape hole that is being made in this wooden block. Let's say it's wood. So like this. Yeah, according to this, the inside gap of that rectangular hollow part that has been caved into this uh, wooden piece. Let's say it's wood. So what's suitable? Yes, internal jaws of a vernier caliper, right? Yes. Is there any other thing to measure the internal measurement? Any other measuring instrument? Yeah, traveling microscope also can be used. Yes, good. But we know that both are using the same principle and having the same least count. Yeah, so it's vernier caliper again, but internal jaws. Then we'll see about the D. D is this, the internal diameter of this hollow part, cylindrical hollow part that is being made. Again, internal jaws of the vernier caliper. Then what else? We have finished the D, right? Then the E. E is what? E is this gap. And they have marked like that. Sorry. This is E. Okay, so we could use the internal jaws, but we are not pretty sure that the internal jaws could fit in, right? So what's the best choice there? Yes, then the traveling microscope, right? So it's okay, like the internal jaws of the vernier caliper can be used here, but we are not sure that, let's say, it's kind of like a hole like this, a cavity. So we can't put those internal jaws, right? Yes. So it's asking the most suitable one. So why we need to bother with the uncertainties, right? We can just try to be traveling microscope. Then the F. Can you see what F? What is it? It's the depth of this cylindrical part. The depth of this part. Yes, good. So we can use the only two measuring instruments that we can use to find the depth measurement. One is the vernier caliper, the depth rod, or maybe the spirometer. Yes. So out of them, it's good to use the spirometer if you can use it, because the least count is smaller than the vernier caliper, then the fractional error will be reduced. But we need to properly stand it, right? There should be a place to properly stand it, and you can send the middle screw. Yes. Then spirometer. You can place the spirometer legs like this, and you can send the middle screw down. Okay, we'll try it. Spirometer. And here comes to the last part, G. Yeah, G is the depth of this part, right? This is the G. Again, a depth measurement. So you could use the spirometer and the vernier caliper. So when it comes to the spirometer, yeah, that's good. We can just let it to stand somewhere here behind the cavity, and you can send the middle screw down. But middle screw is like kind of a little thick one, right? So are we sure that we can send the middle screw? Like let's say we are finding a depth of this. Now maybe like there's a hole here, see? We are not sure that the middle screw fits in to take the depth measurement, right? It should be kind of separated. Here it's better to use the other one, right? Because the vernier caliper, we have flat depth rod. It's not a thick one like this, it's a flat piece, right? Then yeah, we can write vernier caliper depth rod. It's good. Yes, so that I think that gave you a recap of all the measuring instruments that we have learned, right? And it's not only like taking the least count to be smaller, it should be fit to take that reading as well. It should be uh, good enough to take the reading. Sometimes, even though the measuring instrument is more suitable to take that small reading, but we can't use it, we can't properly stand it there. Likewise, depends on the scenario, right? You should be wise and you should have a good idea about the measuring instrument. Alright, so here comes to the end of this tube as well, right? So you will be receiving a new tube very soon. So today we can learn about, we can move to the next part of this first lesson, that is the vectors. Okay, so when it comes to units and measurement, the very first unit, there are two sections of it. The first one which we have already finished up, so unit 1 about measurements. So out of that we have considered about the units and dimensions and measuring instruments. The next and the final part of it is the vectors. That's the end of the first unit. Okay, now we have finished up this and we have finished up this as well. Now it's the last part, the vectors. Alright, let's start the topic, a big topic, vectors. Vectors. Okay, so for the maths class, has the teacher started the applied lessons as well? No, still not? Okay, okay. So luckily the math students can learn this one again for the applied math. I think the very first lesson also for the applied will be the vectors as well. But there you are learning very detailed and very complex scenarios. For the physics we are learning very basic, and I hope this will be also a foundation for you, a good foundation for you to build up that large castle, right, about the vectors for the applied. Okay, so what comes to your mind when you say the word vector? It's not a foreign term, I guess. You learn it for the O-levels? Nope. Haven't you heard of this word before? Okay, okay. So what comes? What's the first impression that you comes to your mind when you say the word vector? Like the vector in that Despicable Me, the cartoon. Have you watched that? Okay, that guy wearing spectacles and the yellow guy. Is that the person or something else? Vectors. There's a similar term comes to this scalar, scalars and vectors. Okay, okay. So scalars are the measurement that we can take only the magnitude, and vector has a magnitude and also a direction, right? That's simply what a vector and a scalar stands for. Another example that we can take will be this, right? When we are taking the length of this, are we saying, okay, let's say the length of this to be around 20 centimeters? So are we saying like 20 centimeters to the north? No, right? We don't say like that. It's just taking the length measurement to be 20. That's it. 20 centimeters. But uh, let's say you are rich enough. Maybe you have a helicopter, right? So what you can do? This is your home, and there's a helicopter pad there. Let's say, and put in that H sign. I think you have seen like the helicopter pads. They have this H sign to land the helicopter, like that. Okay. So we have a helicopter here, like that. Then what you can do, you can just lift up from that home, your home, right? And you can land it to the top roof of this institute. You are coming to the class from a helicopter. It's like that, right? So once you just lift up, you should have a certain direction that we need to move, right? Because it's just a helicopter, so you don't need to follow the road. You can just lift up and maybe you can come straight away from your house to this. Then while you're flying, you should have a specific direction that we need to fly, right? So maybe you can fly to, maybe you lift up from here. Let's say this is your house, or maybe this is the building like there, or maybe this is the building. Um, I'll just grab the eraser. This will be your house, like here. So you just need to lift up the helicopter, and we need to angle it a little bit, and you can straight away fly to here, right? But what if you just fly straight away to this side? You won't be meeting this. Maybe you can fly to other side. So you'll be ended up with Colombo, maybe somewhere else, right? So I just need to show you that there has to be a certain direction that we need to fly in, and also a certain distance. To lift up, maybe it will be a few kilometers, right? 1 or 2 kilometers. From the road, it will be a very lengthy path. But when you have a helicopter, you can have the shortest possible distance that you can have. But also, it has a certain direction. You need to move it to the maybe northeast or maybe to the southeast. I think you have learned for the O levels something called bearing. From here, from north, the angle that you need to fly, maybe take a certain value. That's called bearing. Yes, when you are flying, let's say you become a helicopter pilot, then you should know about this bearing. What's the bearing that we need to take from the north to fly it, right? Again, it has a certain distance, and also which means a length measurement, also to a certain direction. Okay, so vectors mean a certain quantity that has a direction and also a magnitude. Scalar, just the magnitude. Okay, let's write it down. The physical quantities has only the magnitude. Has only the magnitude are called scalars. Are called scalars. We'll write some examples. We say the distance What else? Scalars. Yeah, time. Good. We are not saying like 10 seconds to the north, right? Okay. Time. What else? Yeah. Distance divided by time will be speed. We later on gonna learn about it. And what can I show the mass? Yeah, mass is also a scalar, right? We're not saying 10 kilograms to the east. Like right. Okay. We'll just try this. And to be known, we'll just write something like this. Pressure. Gonna later on learn about it, but we'll just write it to know it as a scalar. Okay. Then about the vectors, we'll just write the physical quantities have both magnitude and direction. Physical quantities have both magnitude and direction. Are considered as vectors. Uh, what are the examples for that? We're gonna learn something about not distance but displacement. Are you familiar with this term? Displacement? Okay, displacement. Then velocity, not the speed, here velocity. If you're like kind of getting feared about it, don't worry, we're gonna learn in detail about this in the next lesson, right? Velocity, and we have something called acceleration, and force, and momentum, something called momentum. Right? There are plenty of examples that we can see for the scalars. Okay, let's copy down. Okay, then let's try the subtopic geometric representation. Geometric representation of a vector. Okay, we'll write like this. A vector can be simply represented using a straight line. Using a straight line pointing with an arrow towards the direction of the vector. The straight line has to be proportional. The straight line has to be proportional to the magnitude of the vector. Okay, so let's say we need to draw a certain vector with the magnitude of 5, right? So and it is acting towards this side. So which means we can draw a straight line with length of the line has to be correspond to the magnitude. Let's say you have 5. Do you know that we can measure the force in newtons? Okay. So we know that the force is now, earlier we have considered force is a vector. So let's say this is 5 newtons. So if you are representing 5 newtons, that means you should use a straight line at least proportional to 5 newtons. That means you can use 5 centimeters to represent the 5 newton vector. And we need to mark the direction, so you can use it like that. And if you are naming out this vector, if you are going to name it, you can put here AB if you are if you are drawing like that, and you can write the AB vector, the length of the AB vector, you can represent like this, AB, and you can draw a line at the top. But let's say the AB is to this side, AB like that. But if you are representing that AB vector, you are not drawing a line like this. Still, you can represent it like this, AB vector. If you write only the AB, it says only a length. We have considered like a triangle, let's say like this. So ABC triangle. So the length of AB we can write maybe 8 centimeters likewise. But when it comes to AB vector, we can't just write 8 centimeters, we need to say that it's a vector. So when it comes to AB vector, it is 5, no? So you can write 5 like this, and you can underline it. Then it's a vector. We know that this 5 is not just a value, we have a direction as well. So we gave it a name, like we can give the names of the persons or maybe the pet, right? Like in my case, my name is Supun and you are Dilu, like, but we have different names, right? Or we can just give it a name for this vector, that is to be AB, and that is having the magnitude of 5 Newton. Got the idea? Okay. So we just write like this. When representing a 5 Newton vector, and put a comma, and you can just draw this. You don't need to draw this one, basically that. Okay, then a new line, right? If the magnitude of the, if only the magnitude of the vector is considered, it can be represented with the modulus, right? So which means if you need to only consider the magnitude, which is 5 newtons here, right? We don't need to consider which direction it is acting as the magnitude. So if you are interested with magnitude only, we can represent like this. This is the AB vector, and if you need to represent that, we are only interested with the magnitude. We just draw two lines, two straight lines like this, not to be much lengthier, but size of the same thing, right? This is called the modulus. Drawing these two lines say that we have considered the modulus of it. Modulus means we are only interested with the magnitude of this AB, which means what? Just 5 Newton. We don't need to consider which direction it is acting. Only the magnitude, 5. Could be to the north or could be 30 degrees to the horizontal. We don't need to consider about it. If you are writing the modulus, that will be only the magnitude of it. Correct? Okay. Right? Okay then. This is called again the modulus. Right. So we write a subtopic. We're gonna consider some different types of vectors. Gonna consider about what is mean by this equal vector and opposite vector, and what are zero vectors. Right? We are going to learn about that. Okay. The first topic will be equal vectors. Equal vectors. Equal vectors. Okay. We'll write like this. If two vectors are said to be equal, if two vectors are said to be equal, following conditions have to be satisfied. Following conditions has to be satisfied. Okay, the first one, now we're going to write out the conditions. Equal in magnitude. Equal in magnitude. Parallel to each other. Parallel to each other. Acting at the same direction. Acting at the same direction. Okay, so it's like this. Let's say I have one vector like this. I can name it as A and B acting to this side. And I have another vector CD. C and D, which is also acting to that side, and the length of this line is equal to the length of this line, which represents the magnitude of the AB is equal to the magnitude of the CD. How you can represent? We are only considering the magnitude. AB vector and the magnitude will be putting modulus. This stands for the magnitude of the AB vector is equal to the magnitude of the CD vector. That means, let's say here this is to be 20 newtons. This also will be 20 newtons. Okay. That represents the first condition, which means the magnitude wise they are equal. That's the first condition. If this is satisfied, and also the second condition, what is that? parallel to each other. So which means if these are parallel, you can see here I have drawn it to be parallel, then I can write the AB vector itself is equal to the CD vector only when these are parallel. Then I could write maybe like this. The AB vector is parallel. You know how to write the parallel thing, right? We use this for the O-level transfer. CD. If the AB vector parallel to the CD, then we can say here this is that condition also satisfied. And the third case, they are pointed to the same direction, right? So you can see here, let's say this is kind of 30 degrees inclined to the horizontal. If this is parallel, this also should be 30 degrees inclined to the horizontal, right? Because we know that the angles between the parallel lines are equal. It could be alternate or could be corresponding, likewise. Okay. So if the directions are equal, that means the length of this one, the direction of the AB has to be equal to the direction of the CD, right? If the direction, there's no way to write it. If the direction of AB vector equals to the direction of the CD vector, then if all these three conditions satisfy, we can say the AB vector is equal to the CD vector. Then we can say the AB and CD are equal vectors. The vectors are equal. We can't say, like, let's say we have like AB to this side and the CD is to this side. Will those two vectors are getting equal? No. Could be magnitude wise same. Here let's say 10. Here also 10. Fine. The magnitude wise they are equal, but they are not parallel and not aligned to the same direction. Then we can't say that the two vectors are equal. Okay. Then we'll just draw this. Right. Then the next one, opposite vector. These are equal vectors. The other one will be the opposite vector. Opposite vector. How we can say a vector is opposite? Yeah. Magnitude wise they are equal, but in the direction they are opposite. Then how we can modify this? Yeah, they should be equal in magnitude, which means if you consider modulus, that should be equal, parallel to each other, but the direction of the AB is opposite to the CD. That means the CD is same as earlier, equal in magnitude, but opposite in direction. Then we call these two vectors to be what? Opposite vectors. Okay. Then we'll write the condition. Uh, if two vectors, are, we write the first condition, equal in magnitude. We'll write 1, equal in magnitude. Parallel to second one, that's parallel. Third one, opposite in direction. Comma, they are considered to be opposite vectors. Opposite vectors. We'll continue the same thing. Since the action of one vector is neutralizing by the other vector, comma, the addition of two opposite vectors becomes 0. Okay, now we can draw that. Okay. Thanks. We can draw it and we'll write it down. No, that is why. It just drawing a arrow represent that it's just a vector. We don't need to like draw it from D to C like this, right? We can represent a CD vector. It's a vector. You can represent it like this way as well, like DC, fine, or maybe CD, DC, whatever it is. The arrow is just to represent that it is a vector, right? Maybe you can write Dilu and write an arrow. That means Dilu in this case it's a vector, right? It's just a representation, not showing the direction. You can write it like this way, then it's fine. DC. right? You write this. Okay. Then the last one, null vector. Null vector. Or we can say them to be zero vector. Most of the time we say null vector, right? Okay, we'll write. What do you feel like when you have null vector? Something null? Yeah, it's kind of zero, right? We'll write like this. All the vectors with a zero magnitude. All the vectors with a zero magnitude. All the vectors with a zero magnitude are considered to be null vectors. It is represented as if you just write the zero, it will be magnitude wise, it is just a zero, right? When you need to represent that to be a vector, it will be like this. Normally we are putting the vector to be like drawing a line underneath, no? If it is a magnitude, maybe the AB vector, it's a null vector, so which means 0 and you put a line at the bottom. Okay, so we write okay. Then the next topic, addition and subtraction of vectors. Addition and subtraction of vectors. Okay, we'll learn it from some examples. Example 1 will be, let's say we have given a 5 vector to this side and also a 7 vector to this side. So when we are drawing that 5 and 7, I think you can see that the length of these lines, to represent a smaller vector, we are using a little line compared with a vector that is representing a large magnitude. We know that when you are drawing, when we are representing a vector, we normally draw it with a line, and that line has to be proportional to the magnitude. Okay, so you can draw it like that. So you have a vector 5 acting to this side, horizontal. You have another 7 which is also acting to the same direction. So what I can do? Yeah, we have to add them. So I can maybe represent it like this. This is that 5 first. From that end, you can draw that the next 7. Both are to the same direction, so we are getting it. To this side, it is 12. 7 plus 5, that's 12, right? Okay. Another one. We have 2 here, plus we have 5. What's the value? Yeah, it will be 7 to this side. Then the third one. We have 12 here, or maybe 10 here. 10 plus, to the other side we have 2. Then what? Yeah, it will be 8. Why? Because I can represent this one 10 to this side plus here to this side it is 2, which means minus 2 to the other side, right? Because we know that vectors have both magnitude and direction. So if you are flipping up the direction, we need to maybe change the sign. Okay, so which means to this side it is 10 plus minus 2. Yeah, as you said, it will be 8. Okay. You don't need to follow this procedure. Straight away you can tell that these two are opposite vectors here. I mean opposite in magnitude, but not opposite vectors. It has to be opposite. You can say that to be opposite like this. When the it's also equal in magnitude. Here the direction wise these two are opposite, which means you can add them, but we can take the difference and put the direction which the large vector points out. Similar to what we are doing when you are adding, let's say, two numbers, 10 plus minus 2. If the signs are different, we just subtract, which is 8, and put the value, the sign of the largest number, right? Here it's a minus 10 and plus 2. Then what? It's minus 8. Okay. Likewise, you can do. Pretty simple. Okay. Let's copy down all these three. Right? Okay. Let's do one more. Like having an odd number is not good, I guess. We would like, okay, so this side it is 2, or maybe any other value that we haven't considered. 6 plus, to this side it is 8. Yeah, give it a try. Yes, minus 2 to which side? Okay, which means plus 2 to this side, right? Can straight away write it like this. It is to be, because you can see the highest vector is pointing out to the left, so which means it's to the left, and 6 to this side. Oh, it's not seems to be that much proportional, but I'll just extend the line like this. Okay, so 6 to this side and 8 to this side, which means 2 to this side. You can write minus 2 to the other side. You can flip the direction to this side, then 2. Correct? Okay. Okay, so it seems to be very simple, right, to do it like that. So where's the hard part? Yeah. Okay, let's say we'll do another one. Okay, we have tried 4. What if we just have the fifth one to be like this? We can have like that. 10 plus 4. Then what? Yeah, 14 upwards, right? 14. And sixth one, let's say the same 10 or maybe 20 plus to this side 8, 12 upwards. Yes. We'll complete that as well. All right. Now, still it feels very easy. Yes, this advanced level part. That's what's coming right up. What if you have given 2 vectors like this? One is 10, same as earlier, plus. Let's say 2 is given to this side. Again, feels very easy. Just 12. What if this to be like this? Then can we write here 12 like that? No, right? Why is it so? Because all the other examples that we have considered, the 2 vectors given are to be aligned to the same direction, which means either to the horizontal or either to the vertical. Could be one up and one could be down, opposite in direction, but still they are aligned either to the vertical or to the horizontal. Here in this case, you can see that one vector it is purely horizontal, the other one is inclined to the horizontal. So in that case, you can't just straight away add it. Okay, here comes the advanced level, right? So how we can add these kinds of vectors? Well, we are going to learn 4 ways of adding 2 or more than 2 vectors, right? So we can use the triangle law of the vector triangle. The second case will be the parallelogram law. The third case will be the resolving. And the fourth case will be vector polygon. So all these 3, the first 3 can be used only for 2 vectors. If you have just 2 vectors to add or subtract, we can use it like that, right? But vector polygon we can use to multiple vectors. If you have more than 2 vectors, 3, 4, 5, 6, maybe 1000, we can use the vector polygon. So it will be multiple vectors. right? Okay, we'll write it down. Following method, following method can be applied to add vectors and get the resultant. Resultant. Get the resultant if the vectors are not aligned. If the vectors are not aligned to the same direction. Okay, we write these for triangle law, parallelogram law, resolving vector polygons. Here we write drawing vector polygon. That's good. Okay. So when you are applying this one, when you are applying this triangle law, parallelogram law, or resolving, we need to know about some trigonometric ratios. So the basic trigonometric ratios we have considered are three, right, for the O levels? Yeah, what are they? Sine, cos, and tan, right? Yes. So for the maths, I guess you are learning about cosec. No, haven't? Not yet. Okay. So you are taking the inverse of all these. So you can, the math students can learn about like cosec, sec, and cot, the opposite ratios of it. But for the physics, we need to learn only these three ratios. And we need to know about some special angles, the value of some special angle, right? So this table should be in your mind until you end your life, right? Not for the A levels. You should learn it for. You should keep it in mind uh, until at least for the end of the exams. But this will be useful for your life as well, right? So we need to know some couple of values. We should especially remember. So we're going to consider about 0 degree, 30 degree, no, 45 degree, and 60 and 90 degree. The values of these for the sine, cos, and tan, you should remember not just for the physics, you should learn it for the make it remember for the maths as well, right? Okay, we'll just draw this table along with me. Okay, are we ready to fill up this table? Okay, so normally if you need to take the sine 30, sine 45 or any other value, the angle, what you usually do? For the O levels, we refer that sine table, right? In the logarithmic book, we have natural sines, natural cosines. You refer from below to the up when you are referring cos, if you can remember. But don't worry if you can't remember, that's totally fine. And also the tan, right? So in the A levels, luckily, we don't need to use that tables much. If you need to use that sine table, that will be only one place. In the third unit, there's something called optics, right? So in that optics part, we only need to refer the sine values, not the other two values, but the sine values. But in the modern questions, they most of the time not asking you to refer the sine table. They will give the sine value if it is a different angle than the. Let's say you ask to find these values. Most of the time we are dealing with the sine 30 or maybe the 30s, 45, 60s and 90s. Could be sine, cos or tan. In those cases, if you can remember these values, I mean you should remember these values, it will be very easy. Without referring to those tables, you can easily substitute to certain questions, right? Okay, so now we're gonna fill up this table. How we gonna fill it? Sine 0. Sine 0, the value of sine 0 is 0. Sine 30, sine 30, it is 0.5, which means half. We are remembering with the fraction. Then sine 45, that is 1 over root 2. The first sine 30 was half, this is 1 over root 2. So what you can do, if you are not like believing me, you can just find out the sine 45 from that sine table. You can do it as a homework, right? You can write the find the sine 45. You have it. Okay, let's see. Sine 45, see? 45 0. 7071. This. Okay. So let's say about the 1 over root 2. Do you have a phone with you? Okay. Shall we use the calculator and see what's the value? 1 over root 2. 1 divided by root 2, see? You can type there 1 divided by root 2. Same answer, right? Yes. So instead of remembering this one, we can remember with a certain fraction. Okay. So that will be 1 over root 2. Then sine 60 will be root 3 over 2. And sine 90 will be 1. Okay, we'll fill it up. Okay, now it's time to fill up the cos value. That's pretty easy. It's just the opposite of this. So when you see cos 0, that is 1, same as this. Then cos 30, that is this, root 3 over 2. And this should be 1 over root 2, and this should be half, then this should be 0. When you are filling it up, the opposite value, you can fill it this side. Okay, let's fill it up. Then the tan values. Tan values are a little bit different, but still we can easy to remember. Tan 0 is 0. Tan 30 is 1 over root 3. Tan 45 is 1. And tan 60 is root 3. And tan 90, for the physics, we take it to be, what is this? Infinity. It's not that the 8 that turned like that, right? We are writing it like that, but it's not the flipped 8. We say it's the infinity. But for the maths, you are not saying to be infinite. Tan 90 is not defined. We can't define the tan 90, the value of tan 90. For the physics, we can take it to be infinity. Okay, these are the values of the tan then. Copy it down. Alright, should we need to remember this? Yes, definitely, right? At least until the A levels, you should remember these values as a fraction, because this being used in wide cases, not just for this mechanics, you are learning it for the, not just for this vectors, we are learning especially for the mechanics, which means we are dealing with force, the velocities and everything you need to deal with these values. Not only that, we are learning it for the third lesson as well, the optics, and for the fifth lesson, that's for the thermal physics, we have some part 2 involving with the sine, tan, cos ratios, right? So it's better to remember, right? You must. And also we have some values here, like you can see they are root 3, root 2, right? It's better to remember the values of them as well. Root 2, root 3, root 5 and root 10. These are the values we are remembering, so that the final answer we can't keep it in the fractional form. Most of the time we need to simplify it until the final value, final decimal. So you can simplify it with these ratios, the fractions. Afterward we can substitute the value and simplify it in the last decimal, right? So the root 2 will be 1.41. Root 3 will be 1.73. It's 141, but 2. At least you can remember up to 2 decimal places. It's better to remember up to at least 2 decimal places. And root 5 will be 2.24. And root 10 will be 3.14. 3.14 is familiar for you. Yes, that's the value of pi, right? 22 over 7. It's not exactly equal to the pi, but at least close enough. So 3.14, yes. If you can remember these values also, the simplification, the final simplification will be a piece of cake. Otherwise, you need to refer this one from the logs, right? Okay, let's take down these values as well in a side. Alright, so that will be your homework for this week. You should remember all these values, right? What you can do, maybe you can first see this one, and maybe you can grab a piece of sheet and you can draw a table similar to this one, and without looking this you can fill up, and also these values. And afterward you can compare with the table that we have drawn right now, and if you are correct you can pretty sure that you can remember it. If not, you should correct it, right? You can do it maybe today evening, and you can go you can stay a couple of days and try to redraw that chart, right? So I'm just sometimes recommending the students to draw it and maybe stick it on the board, but it works for some students. But most of the time what happens, they won't memorize it. Let's say they need to do a certain calculation, then they are doing like that. Okay, we have sine 30, then sine 30 you are looking at that chart, right? But for the exams you're not supposed to bring it to the exam. Any piece of sheet you won't be able to bring it. So yeah, that won't be a good way. So try to memorize. Eventually you can this will be like a part of your life, right? Until that, you need to give it a try to memorize it. Okay, that will be the only homework that you are getting to this week, and we'll see whether asking from the other student if we could arrange an extra class, since we couldn't do it the last FOIA day, right? Okay, so next day we are going to learn about this triangular law, the parallel law, only these two for the next day, and the resolving and drawing of vector polygons on the other day. Then we can finish up these vectors with a nice tutor as well. Okay, so when we are dealing with this, we should memorize this one. We should quickly be able to apply those values. Okay then. Thank you for joining the class. See you on the next day. And if you haven't finished this tutor, you can still take the time to finish it up.